Sounds
Today he's
logical.
going to be talking about his research that is being funded by NASA, in which he's working on developing resilient computer systems that can survive harsh environments. So he's going to be telling us about the great computer that MSU is sending to the moon.
All right,
Let's
awesome.
hear about his work.
Cool. Oh, thank you. So thank you very much. So thanks for the invitation. This is pretty cool. So again, my name is LaMeres, and the title of the talk, I was like, well, Bobcats on the moon, that's kind of the big project that just got funded. But it hasn't actually started yet. So I thought that what I'd do is I'd give you kind of a lead into where we've been working for the last almost 12 years now. I started at MSU 13 years ago. And so I thought you got to put it in context. So most of what I want to talk about is just kind of the research that we've done building up to what's happening. So let's see. But I want to give you a little lead into it. So I always start with what is research and why do it at universities. And then we'll talk about my research on computers. And then we'll talk about the project that we came up with, which is the RadPC, okay? So first of all, just briefly, what do you guys think of when you hear the word research? What's that? Labs, yes. Anybody else? Yeah.
Studies and papers with big words.
Exactly. Long beards and turtlenecks, all that is research. So basically, research is you're creating knowledge, but what differentiates research from just like working at an engineering company or something like that is that you're trying to look at solutions that benefit society that are further out. So if you're building something that's 2 years out, you can just do that as an engineer at like Intel or something like that. But if you're looking at stuff that's like 20 years out, even like 5 years out, it's really hard for a business to do that and make any money because when you look that far out, nobody knows the future. And so what happens is it's really high risk, it's high reward, but businesses can't afford to fail 90% of the time, maybe even 99% of the time, or else they go out of business. And so what we do is research, and what that is where you can take the chance to actually fail, and the payoff is that every once in a while something miraculous happens, and you're able to come up with some cool solution that benefits society. So you got to ask yourself, where does it come from? How do we fund all this research that goes on in our country? Well, it's from you. Okay, we pay taxes in America, and some of that money ends up going to fund research. So if you look at, I don't know if you've ever looked at the federal budget. A lot of you guys do that. Our federal budget in America is like $4 trillion, and of that, $3 trillion of it is already allocated to Social Security and Medicare and Medicaid and stuff like that. And then there's about a trillion left. So of that, half of it goes to defense, but then there's all these different slices in there, and it turns out that about 3.5% go to what we call research. And so we're funding ideas that just are 20 years out, 10 or 20 years out, that have high potential for reward. So it's about $150 billion. So for perspective, annually, like NASA, its budget ranges, it averages about $10 billion a year. And so that's what funds things like, that's what funded the space shuttle, that funds like all the centers and all the stuff that's going on there. They're building, new spacecraft and stuff like that. So all this federal money kind of goes into these pools, and we do these things that have high reward for society. Now one question is, why do it at a university? So we do have ways to do research at like labs. So you have like Pacific Northwest National Lab, and you'll have a building and pay people to actually do research there. But one of the problems is that you have a lab and you'll like focus on something like energy, and you'll have like thousands of scientists there, and then all of a sudden there's a breakthrough and you don't need any more research in energy. So what do you do with those 1,000 people? Fire them, sell the building, and then you continue on, and a decade later everybody goes, oh, that innovation didn't work like we wanted. So then you go back and you're like, all the employees are gone, the buildings are gone, and it just takes forever to ramp that back up again. So we do have national labs in our country, but it's kind of a difficult proposition. So the number has kind of gone down over the years. Universities are great because it's loaded with people called professors who have expertise across a range of areas. And what happens is that since we also teach, we can do teaching and research at the same time, kind of a 50-50 split. And what happens is that if our area doesn't happen to be something that's funded at the moment, we still have a job. So we don't have to like quit the university and go do something else. So we're able to kind of sustain a knowledge base at universities because we do a teaching component. Then the other thing that's cool about it is that we have students here So we need a lot of labor, okay? We need a lot of people to do the work, and guess who that is? That's you. So we have workers, and it turns out that that's kind of cool because you're learning stuff in the classroom, and you got stuff going on in the research lab, and it's like if you're putting that knowledge to use, it helps you learn it more, okay? You know it that when you apply something or you see it in use, you just understand it a little bit better. So that's why we do it at universities. Okay, now back to my area of I wouldn't even call it expertise, just what I am interested in, and that is computers. So when you think of a computer, what do you think? Circuit boards, technology. I'm thinking like, yeah, smartphone, laptop. What's funny when you're a researcher, when you're a researcher, you're always trying to defend why you're doing research. So everybody comes up to you and says, hey, what are you working on? Why is that important? Why is that benefiting society? Computers are kind of funny because everybody understands computers, right? It's like, could you imagine life without a computer? Have you ever gone without your phone, right? It's like, you can't function without it. I mean, people look at it like withdrawals, like they compare it to like, withdrawals from like a chemical substance. It's quite powerful, right? And so you look at these computers, and what's interesting is there's a lot of computers. There was 400 million personal computers sold last year, so that's a lot. There was 1.5 billion smartphones. How many of you are Apple users? A lot of you. You think Apple owns the market, right? No. 1.5 billion phones sold. 1.3 billion of those were Android. Okay? I don't know why. I don't even know why I put that in there. It's just kind of interesting. Okay? So there's a lot of computers. And you're like, well, okay, that's cool. But guess what? There's computers everywhere. Okay? Everything that you hold that's electronics these days is computers. And so you got them in like TVs and printers and your cars. Newer sports cars have like 70 to 100 computers in them. And you think about these things, they're what are called embedded systems. They're not like Intel processors that can run Windows. They're these tiny little computers that are in everything we use. These things, there was 25 billion sold last year. Okay? So this is why computers are so pervasive. When people talk about computers and the internet and stuff like that, this is where people go really crazy. It's like, we're talking billions. There's only 7+ billion people on the planet. So you're talking about computers that are like 4 to 5 computers per person every year being added to our society. So this is a sweet deal. All right, so you're going, okay, so computers are your area of research. What are you looking at so far out? Because I'll tell you, these computers we have are awesome. Wouldn't you agree? I mean, your phone is sweet. And it's like, what is the problem with this? Well, our computers right now have benefited from something called Moore's Law. Has anybody ever heard of Moore's Law? Yeah. So what is Moore? Does anybody know what Moore is?
He's a guy, right?
It's a dude, right? Gordon Moore. He was a co-founder of Intel. Okay? Little side nugget. Anybody heard of Intel? Does anybody know what Intel stands for? Yeah, it's like the best kept secret in society. It stands for Integrated Electronics. So that was the name of the company. And then nobody used that name, and it's just Intel. So anyway, he was a guy, co-founded it in the 60s. And what they did was they built integrated circuits. So they took all these transistors and they put them together on one little slab of silicon. And they made everything on one piece of material. And this was really cool because before that, you had to take all the components and wire them together. So you had to actually build the thing we called a discrete build. But it's like everything was on the same little slab of silicon. And he started jotting down how many transistors were on that slab. And this picture on the left is actually from his lab notebook. And it's he's like, okay, there's 0 on there now because we just started. And then there's 2,000, 200, and then there's 380, and then this and this and this. And he starts looking at the number of transistors that they're able to actually put on a slab of silicon. And I mean slab tiny, okay, the size of a dime. And he noticed a trend right away, immediately within a couple of years, where every couple years, 18 to 24 months, the number of transistors that they could put on a piece of silicon and have them work was doubling. And that has held since 1960 all the way until today. Okay? And this is just amazing because this is why we have the computers that we have today. What happens is that every 2 years, you can expect, this is 50 years since the first microprocessor, which was in 1971. it had 2,300 transistors on it. You look at stuff today, it's got billions, 15 billion transistors on like a GPU card. So it's just unimaginable the number of transistors in there. But it's really dictated the way that we handle computation, because if you think about it, you write some software, you build a computer, you build this chip, and you write some software, and it's okay. And everybody's like, man, your software really sucks. And it's like, why don't you go back and make it better? And you're a developer, you're a coder, and you're like, you know what? I could go back in my office and I could bust my butt for the next 2 years. Or I could go on vacation for 2 years, come back, and the problem will be solved. Because all you got to do is take that same crappy software and run it really fast on the next processor that comes out, and everything's solved. So it has totally changed the way that we approach computation, because we don't really try to do anything that novel. We haven't for the last 50 years, because we're relying on Moore's law to just come along and say, here's another chip that is twice as fast, has twice as many transistors, has twice as much memory. And so it's influenced the way that we design things. Okay, so life is good, right? Enter reality. So if you look at this thing, we got all these lines that are going up and to the right, and they're these trends of like the number of transistors. Well, what's sweet about it is the number of transistors are absolutely doubling on that piece of silicon every 18 to 24 months. But what's happened is that the speed you can run those transistors has flattened. Has anybody noticed that? Like, what's your computer run at these days? Like, you ever heard of like a gigahertz? Yeah, how many gigahertz are flying around in your computers? 4 something? Yeah, what was it a couple years ago?
Probably about the same.
Yeah, about the same. Maybe like 5 years ago it was like 2 gigahertz. And it's like 10 years ago was like when they came out with gigahertz itself. It's and so like when I was a boy, it was, hey, your computer runs at 33 megahertz. Then two years later, it's like 66 megahertz. Then it's like 133 megahertz. Then it's 266 megahertz. And it was just like, yes, yes, yes. And then you guys came along and it's like, no, right? It just all flattened out. So we've been stuck at this gigahertz thing, but that doesn't mean that we're not jamming more transistors on there. We are still doubling the amount of transistors that are on our chips. But what's happening now is it's so hot. We put so many transistors on there that even if it's the tiniest bit of heat, it just melts the chip because there's too many of them. So you have to actually run it slower so that the thing doesn't melt. And then what happens is that they're like kind of crappy, because if you look at what you use a lot of those transistors for, they're for error correction codes. So you have like a gigabit of memory, and you also have another gigabit just to try to correct the errors. And so we're doubling the amount of transistors, but it's not giving us the doubling in performance that we want. And so this comes along, this is my entrance into computer engineering research. It's like, hey, it's over, okay? The party's over. What are we going to do next? So it turns out, yeah, Moore's law is coming to an end. That's the integrated circuit. But it turns out if you look at just computation, that's not the first exponential that's come to an end. Our first computers were built on things like, mechanical relays and then vacuum tubes. You ever heard of vacuum tubes? Yeah, vacuum tubes. They're coming back, right? No, they're not coming back. And then you had the discrete transistors. Then you had the integrated circuit. And so we're coming up to a point where it's like, all right, we got to figure out a new solution to this computation problem. Enter where I come from, which was when I started at MSU, I was like, I'm reconfigurable computing. This is the solution. Before we talk about that, what are other solutions that you've heard about? It's like, what's going to change computing? What's the buzzwords of the day? Quantum computing, absolutely. What are some other ones? Optical computing, absolutely. Those two, everybody's talking about them. They've been talking about that for 30 years. Because when I was in school sitting there, everybody's like, don't even worry about those transistors. Everything's quantum. And then you go to the next class and you take it from an optics person. Don't even worry about quantum. It's all optical. They've been talking about that forever. So it kind of illustrates research though, right? Because you don't want to just go all in on quantum, because what if something comes along and it's like, oh, it didn't work. And it's like all that money wasted and we don't have any other ideas. So we got to do quantum. We got to do optical. We got to have people looking at Moore's law and just jamming more transistors. So there was this other idea called reconfigurable computing. And what this is where you change the hardware. So think about it like this. A computer hardware designer puts everything that could ever be needed in the chip. whether or not you're going to use it. And then you use software to perform a task, and you just use whatever you need. But you do have everything you could ever possibly need on there, okay? But what if you could change the hardware in real time? So when you launch Microsoft Word, the hardware itself configures, gets rid of all the other stuff, and just builds a circuit to run Microsoft Word. It would be very efficient, wouldn't it? Could be. So that's what reconfigurable computing is. If you look at what our chips are today, our processors, they are a jack of all trades, master of none. So they put everything on there you could do computationally. They got an add, you want to add something, we'll put it in there. Multiply, you got it. Divide, you got it. Shift, you got it. Come up with anything, put it on there. And then they all are used on some of the time. But most of the time, they just sit there idle and use up transistors. And when those transistors are off, they burn up power. Okay? So you don't really take advantage of everything at once. It's very suboptimal, but it works great as long as those transistors keep doubling, right? Okay, so here comes reconfigurable computing. Turns out there's these devices, and they're called field programmable gate arrays. Okay? These are actual devices that you can program the hardware. Okay? And it's not magic. It's not like people say you put on a wizard hat and like, hocus pocus, you are an adder, right? It's not magic. It's just they made this architecture, and it's basically just a bunch of gates that you might use for anything you want. And when you program it, you go and you connect the wires using transistors, and when you connect them a certain way, they will give you what you want. And it has benefited from Moore's Law also. Okay, so these things have come along. Field programmable gate arrays, FPGAs, that's the technology, and they exist. They're used in tons of stuff. Okay, they're used all over the place. There's probably some in these TVs. Does anyone remember, you know, the scanners over at the gym? One time those broke down, and so they were working on them, and so they pulled the side off of the scanner, and there was these huge FPGAs, and there was a ton of them. You remember that? Man, we were high-fiving. We were like, yeah, look at this. We're relevant. So these are just normal things that exist. Okay, the idea is this. You take this FPGA, and you just program it to be what you need. And if you need something else, reprogram it. And if you need something else, reprogram it. So the trick becomes this. You got to figure out if that overhead of reprogramming it in real time is too much. So does this work? So we start. So here it is. I'm 12 years younger, and I'm at MSU. I just came back from Hewlett-Packard. I worked there for 8 years. I got my PhD. I'm all jacked up, and I'm like, I know how to do all this. So we start sitting down at computers, and we're coding. And we're looking at plots, and it's very traditional research. You know, just dark rooms and keyboards and consoles and dark screens and just typing, right? And it's like, hey, you want to get up? No way. You know, get those headphones on tighter. And it's just what computer research can look like, okay? And we were getting results, and we started doing papers, right? Remember those? Papers, yeah. I'm like, yeah. I used to build these pieces of hardware for Hewlett-Packard, and now I'm making these papers. And I'm like, you want to read my paper? I'm like, no way. I'm like, that's okay. So I start doing traditional research, and I'm like, this is so something, right? I mean, it's not what I expected, but at least I know how to do it. At least the paychecks are still coming. And then I ran into some colleague from NASA, okay? Future colleague. And he heard one of my boring presentations about, you know, just the computation and reconfigurable computing. And he says, man, you know what? This idea that you're working on could actually be applied to flight computers. I said, oh, that's kind of interesting. Tell me more. So this was, like I say, 12 years ago. This was when a program called Constellation was happening. This was the approach by NASA to get to the moon and Mars. Okay, so they had all the spacecraft, they had all these rockets that they were working on, and they said, what do we need out of our flight computers? And they said, okay, what are the requirements? First one is it has to be light, okay? The way that spacecraft are built, like the big dog stuff, like from NASA, they put a computer for everything. So it's like launch, they got a dedicated computer, takes off. Then they toss that thing off, and it burns up or falls in the ocean. Then they got another computer that takes it into orbit and like keeps it into orbit. And then when they're ready to do some science, they bring on another computer. And then they're ready to come into the Earth, so then they jettison something, and they have another computer for that. They got another computer for the radio. And they just have loads of computers in here, each that do the very dedicated task. So we said, you know what? what if you could get rid of all those computers and just replace them with one computer and just reconfigure it on the fly? So I was like, oh, this is sweet. This is what reconfigurable computing can be used for. They need to be low power. I said, we got that. You got 10 computers. Just by the virtue of using one computer, you'll save power. Got that. Then it was, they have to be high computation. It's like, that's the whole point of reconfigurable computing, right? It's supposed to be better than the jack of all trades, Moore's law thing. It's like, all right, got that. Then NASA goes, they have to operate in the presence of harsh radiation. It's like, what'd you just say? Never even heard this term before, right? I'm in a cube, dark, headphones on, typing, right? And then they're like, you need to build a computer to operate in the presence of radiation. We're like, you got to be kidding me. So we start learning about radiation. So we put down the keyboard and we start looking at what it's like to be in outer space. So you've heard of, has anybody heard of the sun? Okay.
What's that?
Let me tell you, it is a big ball of gas, right? And it turns out there's a lot of them. And these things are making radiation, right? It's great because some of the radiation is heat. But it turns out, so you ever heard of like nuclear fusion? Yeah, so you kind of learn about that. You got all this hydrogen. I'll give you the computer engineer's version of nuclear fusion. So you got hydrogen, right? And there's a bunch of it. And they're sitting there, and there's all this gravity, and they get together as a big ball. And there's so much energy, and there's so much gravity that it actually takes that hydrogen, and it just like boof, and it makes helium, right? So it actually just boofs together, right? But it's crazy because like the matter, it's helium is a little bit lighter than two hydrogens. So you actually take some of the energy and you convert it, or take some of the matter and convert it to energy. Has anybody ever heard of that equation that relates energy to matter? What is it? E equals mc squared. Yeah, everybody knows that. But it relates matter to energy. But there's a c squared in there. Anybody know what c is? Speed of light. Man, huge number. Huge number times huge number is huge number. It's a huge number. So what happens is you expect this to happen. Hydrogen, hydrogen, yep, hey, helium. And then here's some energy. Oh, sunlight, right? That's what it feels like. It's not like that at all. It's like this. Just explosion, right? So now what you have here is that nice little helium that was like, oh, now I'm helium. It just gets blown to bits. Its neighbors get blown to bits, and everything comes shooting out of this ball, and you're like, oh my gosh, what's going on? You got just regular helium nuclei with nothing on them. No electrons, and they're just flying off. And they're like, I don't have my electrons yet. You're out of here. And then you got the electrons going, wait, and they're flying out. That's alpha and beta, right? Everybody's heard of that. But you know what else you have in there? Well, you've got a whole bunch of stuff. Yeah, you hear like, we got gamma, and you got X-rays, and you got that. You remember in Chem 141? Are anybody in Chem 141? So right now, you maybe have got there, but you're going to learn about this thing where when you have an atom, and you have this electron orbiting it, whenever it like moves out of one orbital into another, you can put energy in, and the electron it's energized. Then when it drops back down, it gives off electromagnetic energy. Electromagnetic energy is like a radio wave or like your Wi-Fi. Okay, it's not mass traveling through. It's just a pocket of electric and magnetic energy, and they're just okay. And it turns out that the frequency those are at depends on the size of the atom and which orbital you're in. But anyway, imagine that you take this nice little guy and you have an electron going doo 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 doo, and the little energy's going off, and then and it's gone. You've got all sorts of frequencies of energy flying out of there. So you got X-rays, you got gamma, you got all sorts of stuff. Ultraviolet, luckily, you got not luckily, but it is handy. Okay, it warms us up. So you got all this stuff cruising along. And then you just take the nucleus and just blow that up too. So you got protons coming, you got neutrons coming. That's not natural, but here they come. And then you have other junk that was in the sun to begin with. You get like iron. It was just sitting in there, and it gets blown apart. So here it all comes. And it's just like, holy cow, this is a lot of stuff coming at us. So you might be wondering, how are we even surviving right now? Does anybody know? Yes. That's one of it. Okay. Yeah, so let's talk about this before we do that. What happens to a computer? So you got a transistor. Anytime that radiation hits it, it flips the bits. Okay, so it actually, you got ones and zeros, and they're nicely going tick, 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 depending on what you're doing. I'm adding. Here comes radiation. Boom! The bits just go flying around, and they're like, oh, what happened? And all of a sudden, your calculator doesn't work. And you're like, man, that sucks. Or let me put it in terms of you'll understand. You're watching Netflix on your phone, and all of a sudden, it starts glitching. And you're like, I can't take this anymore, right? Well, it turns out that radiation is actually striking the circuits that are in your computers, and it's messing them up. One of the things that happens is you actually take that nice silicon we were talking about and actually just change the material itself. So the radiation will, some types of radiation will come in and just hit it and just change it. And over time, the thing stops working. Other types actually go flying right through and actually flip a bit. You know, computers, we always talk about ones and zeros, binary. Well, just imagine you want to be a 1 and you become a 0. Then your computer crashes. Okay, so that's the type of second issue that we have. And so we call them total ionizing dose, which is where the material gets messed up. Single event effects is where you just flip a bit. Okay, now, how are we not dead? More importantly, how come our computers work right now? Okay, so we're sitting here, and we got our computers, and we're all happy, and we're watching Netflix, okay? How come they work if we have so much radiation coming in? Someone said ozone layer. Is that what you said? Yeah, ozone layer. That's true. Here's what's happening, okay? The Earth is a miracle, okay? It is unbelievable. There's a whole lot of protection going on here. First of all, magnetic field. The core of the planet is all this iron and nickel, and it's just churning, right? And so you're churning all this magnetic material, and it's causing these magnetic field lines to come out of our poles, and they protect us. So it goes out the North Pole, goes into the South Pole, and so we're protected within this magnetic field. And what happens is this magnetic field, when these charged particles come, it'll actually deflect them, and it'll go shooting into the poles. And it'll also sometimes just shield us completely so that they go by. They'll just hit us and like surround and then, or go around and then like on they go. So this is like a big deal to have a magnetic field. Some things that don't have magnetic fields don't have life necessarily. Like they talk about Mars, they think, man, if that had a magnetic field once upon a time, there might have been life there, but there ain't no churning in its core, so it doesn't have one. Okay? The magnetic field, have you ever heard of the Van Allen belts? Yeah, they actually named them because they were pretty consistent. So you can look at these belts, and it basically talks about where the radiation is getting deflected around the Earth. And what's neat about it is that if you know where they are, you can put computers up there, so like satellites, the International Space Station. So the International Space Station, we try to fly that like right below the magnetic field lines so that we're not getting hit, we're protected. Anything that gets through, and stuff does get through, here comes the second shield we have, which is the atmosphere. And this takes the heavy stuff that can blast right through the magnetic field, and it actually hits the oxygen and nitrogen, just ding, 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 and over 100,000 feet, it actually slows down so that we got Netflix, okay? Now, we still can get hit with this stuff. They say that if you fly from like LA to Tokyo, you're up high enough that you don't have enough atmosphere that you're like guaranteed that your computer will glitch due to radiation. So we're protected on the surface, but it does protect our computers and us. Yes?
Does that slowly damage computers over time if you're flying a lot?
It would, but it would take a long time. It would take a long time. Okay, so now we're sitting here, and you got to say to yourself, well, you're working on this problem that's been solved, right? You got the International Space Station up there, you got satellites, you got Mars Curiosity, you got all this stuff that's happening. You go, how are the computers working in space right now? So it turns out you can do stuff to the computers to make them what we call radiation hardened. Okay, so you can go in, take that silicon, and you can do wacky stuff to it. You can redraw the transistors a funny way. You can embed different materials in it so that it's not as susceptible to the radiation strikes. And you can change it so that it can resist it. And so you look at me and you say, well, now the whole problem is solved because now you can build a computer that operates in space. So why is there an issue? Well, they're expensive. Okay, Mars Curiosity has a processor on it called a RAD 750. Okay, $200,000 per chip. And they said, let's put 2 of them on there, right? Sometimes these government missions can get very expensive because they're like, we're designing not for cost. We want science, we want exploration. We're just going to go for it. The other thing that happens is those techniques I talked about, as soon as you start messing around with it, then they get slower. Okay, so they start getting slower, and it turns out that if you look at like a radiation hardened chip compared to its commercial counterpart that's the same size transistor but doesn't have the wacky stuff done to it, it's about 10 years behind. They say 10 years, is that a big deal? Is 10 years a big deal? Have you ever turned on a 10-year-old phone? The thing don't turn on anymore, does it? If it does, it says need to update, and then the thing just, it's gone, right? So 10 years is a pretty big deal in the life of computers. All right, you know what? Want to know another problem when you mess with those transistors? The whole thing with Moore's law is that you're making the chips, you're making a lot of them, and you're using them for general purpose applications, okay? You remember that 25 billion number, okay? You want to know why our phones don't cost $1 million each? Because we sell 1.5 billion of them a year, okay? If you make a lot of something, the cost goes down. So we're talking about having 25 billion embedded computers. How many Rad 750s were used on Mars Curiosity? 2. Well, wait a minute. They needed a spare Mars Curiosity, so we're talking 4, right? So these things are amazingly expensive because there's no volume. If everybody decided we needed radiation-hardened processors, we'd sell 25 billion of them, and the cost would come down, but it's not happening. So that's the issue. We need cost as one of our variables. So this is new. So now NASA's going, we can't have multi-billion-dollar missions anymore. We need more missions, and we need them to be cost feasible because it's just we can't do these things that take 10 years and cost $2 billion anymore. So this is a new variable that we have. All right. Now we switch to our idea at MSU. Okay? We needed an awesome name. Some would say a radical name. And we came up with RadPC. Okay? Now I know your adrenaline's going. Half of you are like, yes. The other half of you are like, did you just rip off Rad 750? Don't worry about that, okay? Our technology is called RadPC, and here's what we do, okay? We take an FPGA. These things exist. You just get on Amazon and buy a bunch of them, okay? They show up, right? They don't have to build them, they're there. Since it's an FPGA, you can configure its hardware. So you can do reconfigurable computing, but it's also cheap. Okay, these things are cheap. They're a couple bucks, maybe 10 bucks. Some of the big ones are 50, maybe 100 bucks, but they're not $200,000. So they're cheap. And this is good, okay? What we found out, and this is one of the things that just happened. We didn't do anything. The transistors get smaller and smaller and smaller. Remember that effect I was telling you about where the radiation like changes the material? It turns out that kind of goes away when you get smaller and smaller. And it has just to do with the radiation comes in and it just blasts these electrons, positive and negative charge apart, and then they ultimately come back together. Well, it turns out that if you're really big and you're like a big insulator, you go, and then you're like, oh man, I'm really away from you for a long time. Oh my gosh, this insulator's big. I can't get back to you. It's like, oh, I'm sorry. Sorry, darling. I ain't making it back. And all of a sudden you're stuck, okay? So what happens is that in those big transistors, you would have charge that gets stuck in the insulators. You take an insulator, it isn't supposed to conduct electricity, and you start putting charge into it, it becomes a metal, and then it conducts electricity. That's no good. So now you have a situation where you're screwed. Well, what happens is when you make the materials really, really small, you can come and blast it with radiation, and it goes, it's like no problem. So there was no like long-term damage because statistically you didn't have the probability that it was going to like get stuck. So all you got to do is buy one of these FPGAs that has a transistor that's just small enough, and that effect goes away. But the other problem is that those bits I was talking about, the ones become 0, 0 becomes 1s, those things go nuts. So now those are bouncing all over the place. So we came up with an idea, and the idea was that we have this FPGA. And it's, you can put a lot of stuff on these things, okay? So we said, why don't we put a computer on there? We can do that. That's legal. We're just programming it to be whatever circuit we want. Why don't we put 3 of them on there, and we'll run them in parallel. Now, I'm not talking parallel processing to get advanced computation. I'm talking the exact same thing, and we'll just check the outputs of them. And if they're all the same, life is good. What happens if one gets faulted? It's different. 2 are the same. So let's just keep marching. And that's called triple modular redundancy, TMR. And this is not something I made up. This is like NASA handbook. They're like, you want to build space computers? Read this. Except it's more like, read this. And everybody goes, I'm never going to read that. And it's like, well, don't tell anybody. But TMR is how you do it. The problem is when TMR happens, you still got to fix that guy that got faulted. So you still have to like produce the output. And then you're going to go, okay, let's just stop for a second, take a breath. Let's reboot that guy, and let's bring him up, synchronize, and go. We said we can speed you up because we can put a spare on there. So instead of actually taking this thing that went down and then halting the entire system, what we'll do is we'll have one ready to go. And we'll go, take this guy that's a spare, continue in TMR, and go, and just do your thing. And then we'll come in the background, and we'll program that little buddy back to its normal state. And then all of a sudden, ding, you got a spare again. And it turns out that it's quicker to repair that than it is to actually halt the entire system and bring all of them back up again. So that means you can be more reliable. So we said, we need TMR plus a spare. And so what did the students do? They said, we need TMR plus 99 spares. And it was like, holy cow, how many spares can we pile on here? And it just kind of ran away. So then what happened was we learned you really only need one spare. So we built a lot of systems that had like 9 spares, and we had a bunch of 16 spares and all this stuff. And we ended up just we only need one spare. But that's the big magic. We call it spatial avoidance and background repair. Now, why is it spatial avoidance? I'll just be honest with you. This is all marketing. So everybody, that thing I did, that's pretty self-explanatory, but you don't explain it to that when you talk to NASA like that. You go, oh, radiation here, I take my processor, woof, over there. And then it's coming in over there, woof, over there. Oh, that one got hit? Replace it. And you just make it sound awesome. And it really is, I guess, spatial avoidance, because you did get hit in a certain location, and you brought on other circuitry to replace it. So it is true that that's spatial avoidance. Background repair is true too, because you come in the background, and what you do is you reprogram that. Okay, turns out we didn't come up with this either. The space shuttle had this. So this right here is these yellow squares. Those are processors. And it turns out they had TMR plus 1 spare from the space shuttle. And I was like, what a great idea. So what are we doing that's new? Really all we're doing is just doing it on a modern FPGA where we can dynamically put in different cores all the time. So if they come to us and go, hey, I want this particular core right now, and we build it for them, and then they come back and go, oh, I want a different one, we can just put in a different one. Okay? So there's precedence for it. Okay, then what we do is we have to do what we call memory scrubbing. Cool technique for basically just take the memory and we compare it to a golden copy of it. So we do have like a backup of the memory, but we keep it in something that's pretty resistant to radiation, like fuse-based memory. And then you just go line by line and make sure that everything's cool. Okay? And we do use error correction codes just like a normal computer. Okay, that's the idea. One of the reasons you do it this way is because it becomes a flow problem. So if the radiation's coming in, if you're able to replace those cores and repair them fast enough, and you can outpace the incoming radiation, you're good forever. Okay? And so what happens is that even if you can't outpace it, all you got to do is have enough spares so that you can swap them in, swap them in, swap them in, and ultimately you can stay ahead of it. Radiation isn't like just constant. It's just like whole bunch, and then it's like nothing. So it's a matter of like a lot and then a lot and then a little. So you do have time to just survive the rough stuff and then kind of take a breath and get back in there. So if you have enough spares, you can keep ahead of it. We learned you only need one. But that was many years to try to get there. Okay. So we started building a model, and so we did all this math stuff. We used Markov models. Some of you probably have messed around with those. And so there was a mathematical way to model this. We showed that our idea was an improvement to the NASA handbook. We said we can show a better reliability than TMR alone. And they said, all right, let's do something. Let's build it. So now we take that same idea from 12 years ago. And what we do is NASA has this thing called Technical Readiness Level. You ever heard of that? TRL. And when they adopt a technology, they just don't take something that you built on your bench that day and go, yeah, I'll put that in the space shuttle. Saying, no, I'm not having it. You got to prove that it works. So what you do is you have to show that it is advanced up the TRL scale. Scale goes from 1 to 9. 1 is everybody in this room has a TRL 1 idea. You walk up to a whiteboard and go, you could do this. That's TRL 1. Okay? You start putting some math behind it. That's about TRL 2. You start building stuff together, TRL 3. TRL 4 is where it's like, you better fly this thing and show that it works. And you march all the way up. TRL 9 is where you've been space proven and you can be adopted. So then when they say, I'm going to build a new satellite, they go, you know what? You can pick Rad 750. you can pick RadPC, you can pick this other thing, and so you're on the list of approved parts. So that's what this all started. This is what has happened over the last 10 years. So we start. TRL-1. The Montana Space Grant Consortium, which is a statewide agency for NASA, there's money that's allocated to each state so that they can sponsor space research. They said, you got a cool idea. I'm going to give you some seed funding to build a little something, but more importantly, get on an airplane and go talk to everybody at NASA and let them know about what you're doing and see how they can guide your research. So they said, this is a cool idea, cool enough, let's fund a little bit more to actually do something cool. I said, you know what's cool? Let's put it in a cyclotron, okay? Anybody heard of a cyclotron? Yeah, we went down to Texas A&M in like this 1960s bunker the size of this building, and they got all these people underground just shooting these beams of like radiation, and then you can go in there and you can put your hand in there and your finger gets shot off. And you're like, all right, now I'm going to put it in my computer. It's a little safer than that, but it's intense, and you put it in there. And we were like, man, this is going to be so cool. We build it, and we go down there, and guess what we discovered? The highest energy beam that they could create couldn't even get through the aluminum cap of the FPGA. And we're like, this sucks. So he said, no, we'll salvage this. We'll put a little sensor in front of it, exposed sensor, and when it hits the sensor, we'll just pretend that the FPGA is getting hit, and we'll dance around. So we were able to like make lemons out of lemonade. That's not the saying, is it? We were able to make cool. So we actually got through this, and it was like, okay, that's pretty neat. So they said, even though it was kind of a failure, they said, all right, let's do something different. Let's start flying, okay? So they funded some projects to build balloon payloads. The first thing you do when you fly is balloons, okay? Weather balloons, they're about the size, they're like this big. You can take a tank of helium out in the field, fill them up, launch them. Weather Service does this constantly. They're putting up thousands of these a day to get information on the weather. So you just tie to this rope and you fly it. It pops, comes down, you got to find it. So we flew a lot of those. We flew on a NASA balloon. I don't know if you can see this. This is a NASA balloon right here. This is a semi right there. Okay, so this thing's as big as Cobley Hall, and it gets like 10 times bigger once it gets up to 100,000 feet, and this floats for like 12 hours. They got ones floating right now that can go like a month. Have you ever heard of anybody say, hey, I saw a UFO? Yeah, it's always these. Like, I'm not just usually, always. You can correlate everybody in New Mexico saying, I saw a UFO with these balloons. In fact, yesterday, there was a news story that said, UFO sighting in New Mexico. And it's like, it's another one of these NASA balloons. It's like no one ever learns. But who cares? It's fun. It's like we're going to get a UFO sighting. Okay, so we flew this thing. We got some sweet pictures. It turns out that if you get up to 100,000 feet, you're outside of the blue. You're in the black of space. You're not technically in space, but you can get some sweet pictures like you are. Okay, then they said, let's go to space. So you go on a sounding rocket. Sounding means you go up, but you don't achieve orbit. Okay, you don't go up and get into orbit. You just go up and come right down. A sounding rocket is a missile. And I'm not kidding, missile. These are former missile bodies that weren't used. So then NASA bought a bunch of them, and then they said, all right, we'll take this missile, and we'll put a bunch of science experiment on there, and then run, and it's gone. And they're awesome, okay? So we had a couple good experiences on this. See that little thing on the left? That was our computer. That we've screwed it down pretty tight. That thing just went like this. So the gravity was it breaks like 5G before it's even off the ground. It goes 0 5G and then it's gone. So it's pretty awesome. Good pictures. So then we got a big break. We got a chance to demonstrate this on the International Space Station. So we were able to go up to the International Space Station and build something that plugged into the space station, and it operated for a year. The space station is awesome because they have power. So you basically just go up, plug in, and then we looked like a thumb drive. So we logged all our data from radiation strikes to a thumb drive, and they would email me the data, right? So you think about science. How does NASA do this science? I'm going to get access to the secret portal that's in a mountain somewhere, and I'm going to have to go there physically and get like this tape drive and carry it out. And I'm like, what do I do? Where do I get my clearance? And they're like, we'll just email you the file. I'm like, all right. So we did that for a year in 2017. And then we said, all right, let's start building standalone hardware. So we started building satellites, small as in size of a loaf of bread. And it took a few different funding sources to get enough money together so we could hire people and actually build it, because this is where it gets expensive. And so we have this mission. We came up with a name called RadSat. Yeah, pretty sweet, isn't it? Yeah, it's pretty rad. You can see this theme of all the names. So students build it. That guy on the left in those two pictures, that's Chris Major. He's right there. So he's one of the students that worked on this. And that was the concept. This is RadSat. So if you look at that, you can look below this dot. See that M on there? So that's the logo of Montana State University. And so we're like, I'm not just putting a satellite up, I'm putting a logo on that thing, and we're going to be awesome, right? So we said, all right, launch it to the International Space Station. The way they do these, a lot of them, is you actually go to the space station with like water and food, and then the crew takes you out. You're in a duffel bag. And then what happens is that when you're ready to go, they put you through the airlock, and the robotic arm comes and grabs you. And then they take you out, and you're in a box with a spring in it. And then they go, all right, you ready? I say, yep. And they go, click, and the door opens, and your satellite gets pushed out. And then you orbit for a little bit. And what they do with the small stuff is actually push you down. So you only get, like, sometimes you get like 3 months, maybe 12 months, 24 months, because you burn up. So you have to make sure you don't have, like, you can't have titanium in there because that'll make it and like hit somebody. See, if you're aluminum though, it just burns up. So it's safe. And so we put it into orbit using a NanoRacks CubeSat deployer, which is that box I talked about. NanoRacks is just the company, but this is a good time to pause. Do you see what I'm seeing right here? That logo. That is MSU's logo coming out of the International Space Station, being put into orbit. This picture, no one can believe that we got this picture. This was taken by a crew member on the space station, and he's in the cupola, which is the one that has the glass. And I'm talking just a digital camera. And he caught this. And we were like, oh, this is the $1 million picture. I'm going to use this for the rest of my career. There it is, and there it is, and there it is. And I'm just like, yeah, this is so cool. So I'm still milking this. You're going to come back in like 30 years. I'm going to be, look at that! There it is, Sonny! When I was your age. You know what else we did? 125th anniversary of MSU. Put all the graduating names of our anniversary year on metal plates and stuffed it inside of that. So they all flew into outer space. They're all orbiting Earth right now. Made a big announcement at commencement, and it was like, everybody's like, wow, that's pretty cool. I was like, more than pretty. Jeez. All right, so there's RadSat. And then we actually operate it. Has anybody ever looked at those buildings over there and seen those sticks on top? They look like, you think of an antenna, it's like an antenna. Well, our antennas look like these sticks. And we operate all of our satellites from over there. We actually have 9 satellites in orbit. Not all of them work, but we've gotten 9 into orbit, and we have 2 more going. Okay, so there's actually 2 RadSats. Okay, so there's RadSat 1 and RadSat 2. RadSat G and U is what we call them in the lab. But one of them has the M, so what do we do with the second one? Cat head. Right? So we got the cat head in there. When we stuffed the names of our team on there, so we have some stuff in there, but we didn't do like the student names that didn't work on it. But so this is the 2 RadSat missions, and you got to be stepping back and going, holy cow, you guys have done a lot of stuff in 10 years, because that's when we started building all this stuff. Now remember, I come from Hewlett-Packard, and I'm like thinking I'm awesome. I got a PhD Hewlett-Packard, and I'm like, I was building real hardware, I was turning screwdrivers, and I'm like, I'm gonna do awesome up here. And guess what? It has been 13 years. I have not touched a screwdriver. I have not written 1 line of code. My students have rarely even let me in the lab. Every single thing that has been done by MSU students. And it's not just like the art, the design, everything's designed. I come up with this kind of idea, and these guys just run with it and build it, and they fly it, and it's just unbelievable. So we've had almost 150 students from freshmen to PhDs work on this project. So you're like, what's next? You know it. Going to the moon. In a miracle, we got selected to demonstrate RadPC on the surface of the moon. And this is very recent. So I have the kickoff meeting for this next week. Okay, so this is hot off the press. So we got chosen to go up there and be a technology demonstration. So what's the concept for this mission? First of all, The NASA mission is called Artemis. Okay? Has anybody heard that? Yeah, Artemis is what they're calling going back to the moon. I want everybody, I don't know if you can see it, and I'll squeeze in here. This was the project that went to the International Space Station. You know what the name of ours was? Artemis. Yeah. Should have trademarked that. But anyway, so here we are with the Artemis mission concept. So what do you do to get to the moon? Okay, first of all, you go into orbit. Okay, you go up, you don't just sit around Earth because you'll come right back down. You have to get like 6 to 10 times away from the Earth, you know, the radius of the Earth, before the gravity doesn't pull you super fast in. So you orbit it. So you go up a little bit and you just go really fast. Then you can sit there. So the first thing you do is you go into orbit, and then what happens is you brake it and you go and you go out to the moon. And then you start orbiting the moon, and then they're going to drop down and they're going to start putting stuff on the moon. So here's the phases of the Artemis project. It's a little hard to see in these small screens, but they're going to do stuff like take the manned spacecraft and they're going to go around the moon. So that's coming up pretty quickly. Then they're going to go and they're going to drop like technology there. So they're going to have these landers that drop, and they're going to try to do stuff like just see if they can drop, and if they can, try to test out certain things like sensors of the radiation environment and all that sort of stuff. And then they're going to just start dropping stuff so that it's there, food and water. And then they'll have a manned presence on there, or a crewed presence. Sometime, you know, they're hoping, you know, 2024 that we have people up there. Okay, and if you think about where we are part of this thing called the Commercial Lunar Payload Services. So what they did is NASA selected all these commercial companies. There's like a half dozen, maybe 8, and they said, I want you to build a lander. And the landers they're not huge. They're like this big, and they're going to be carried out to the moon, and then they have to figure out a way to like actually orbit and come down and land. So they said, if we're going to pay for that, NASA's building a rocket, the companies are building these landers, and they said, let's strap on a bunch of technology. So they looked at a whole bunch of people who had technology that's been proven, and they said, let's bolt a bunch of that stuff to the side of these landers and get the biggest bang for our buck. So that's where we come in. So we are actually going to be bolted to one of these landers, and then we'll be carried to the moon, and then we operate, and then life is good. So that is what we're talking about doing, and you're going to be asking yourself, how in the world are we going to do this? And it's like, with you. So this is another one of these, is all this is going to be done with MSU students. So there's not going to be any professors in there turning screwdrivers. This is like, we got to team up, we got to staff up, we got to train up, and we got to deliver this real piece of hardware that's going to go to the moon. Another thing hot off the press, we've got some outreach events that we've just came up with. We're going to have a statewide naming competition for high school and below students, and they're going to name this mission for us. So no more RadPC or RadSat, I guess. I was going to call it Lunar Rad or Rad Lunar or something with rad in it. Turns out, nope. We're going to let some K through 12 student name it, and whoever gets chosen as the name will get an all expense paid trip to see the launch of whatever the name is. And so we're going to launch that, or we're going to start that event in, a couple weeks. So that's what I'm all about. And so if you have any questions, I'd be happy to try to answer them. So.